So, for our second talk of the morning, it's a pleasure to be presenting Conan Leung from the University of Hong Kong, who will speak on Instantons and G2 G.
Thank you very much. And first of all, it's a Chinese university. They haven't, yeah. It's a University of Hong Kong.
The best one.
The one. I don't know what to say.
I just said University of Hong Kong.
A University of Hong Kong. Yeah. Well, first, I'm so honored to have this opportunity to speak in the Berkeley conference. And for me, this is really such a great pleasure because besides this amazing book on speed geometry that we heard so much yesterday, and another paper that I read from break all the time is this, it's like a thing that I have to go back and read it over and over again, is this calibrated geometry. And you certainly will hear many more talks on this. And so today I'm so happy to have this opportunity to be speaking in front of the founder of this whole subject, Blaine and risk, and also many important people who have made so much contribution to this beautiful subject. And first of all, it has it's a beautiful subject and have important applications in minimum submanifold, and also recently it becomes such a central piece in mathematical physics, string theory, and theory, and so on, as we heard from Conan yesterday. So I'm only going to give you some simple few observations that I had over the years on G2 geometries. So to be the first speaker talking on this subject, maybe I should start by starting with the basics. Something as basic as okay. So can you all see? Okay. So G2. So I'm going to speak from two perspectives. Why G2 in math and in physics. So in mathematics, the way that I look at it is there are all this basic algebraic structure. So algebra. So in non-algebra, there are only four of them, as we all learned. It's a real complex cotangent and octonion. And octonion is the largest algebra we have known. It's 8-dimensional. And the symmetry of this very rich algebra is a Lie group, it's called the G2 group. And that's G2. And in particular, it adds on the octonions, but it's the algebra automorphism, so it fixes the identity one. And therefore, it adds on its perpendicular complement, which is 7-dimensional. So it adds on the imaginary part of the octonions. This 7-dimensional space will play the almost important role in our talk here. Well, in physics, lots of study is on string theory in 10-dimensional space-time, and one common way that we compactify it is we compactify on a Calabrian free-form. So why is a Calabrian free-form? So we compactify on a Calabrian free-form. Why? And Calabrian free-form is the same as the holomorphic group is in SU3. And there are many string theory, and they turn out that they are all related to each other by different dualities. And later it was realized that one can have a unified theory if we go to 11-dimensional space-time. And in this case, our compactified space is G2 manifolds, 7-dimensional. And there are also further theory, so-called theory of fathers.
G2 manifold means the holomorphic G2.
Yes, I will come to that. As I promised you, I will be completely separate, except the technical part. So let's also add theory. It's on spin 7 manifold. And spin 7 is kind of the twin brother of G2. It's kind of like you can realize it's some kind of twisted automorphism of G2, of the octonion. So it's not exactly automorphism, but there's some twisting. So it's a related. So to begin, let me give you a picture of how people look at like string theory, which which is more people are more familiar with. So let me start with a Calabi-Yau manifold, Y. Okay. And so this is the box is the Calabi-Yau manifold. And in string theory, one look at so-called open string, so the holomorphic curve. Okay, string move around and give you a Riemann surface, so that's holomorphic curve. And there are two-dimensional submanifold in Y. And also we will look at the open string. And open strings, when you move around, then the Riemann surface will start to have boundary. And the boundary has some boundary conditions, and physicists call those boundary conditions ring. And in the Calabi-Yau case, the ring has turned out to be exactly those calibrated submanifolds invented by Ring. And they are sometimes you also have to couple with a unitary flat connection over those special branches. Because one of the exciting study of Calabi-Yau manifold is the duality, so-called mirror symmetry, and that relate symplectic geometry and complex geometry of the mirror manifold. And now we go up one more dimension. Doesn't look like so, but I cannot draw 6 or 7 dimensions. So there's one more dimension everywhere. That's what it is. So same thing. Everything is the same. We go up one dimension. So in dimension 7, we have G2 manifold, which I will define in a moment. Instead of holomorphic curve, 2 dimension, now we have 3-dimensional submanifold. I mean, all these notions are defined, created in this important paper on calibrated geometry. So this, I'm going to call it Instantons, as you will see in a moment. The reason I call it. So we'll look at 3-dimensional submanifold inside G2 manifold, and they satisfy equation similar to the holomorphic equations, and this is called associative submanifold. Similarly, you can have a boundary value problem where the boundary lies inside 4-dimensional, we call it ring, which is a coassociative submanifold. And one can also couple this with gauge theory. For example, in the 3-dimensional, we can include a flat connection, so the transharmonic. And in the 4-dimensional, coassociative submanifold, one can couple with the anti-self-field submanifold. And one of the difference between G2 and Calabi-Yau is one might in fact has richer structure, more structure in G2 instead of so-called duality, meaning that two theory are equivalent. One might hope for a chirality theory. In a way, chirality is one way one can define the orthogonal structure in a dimension. So for most people, low-dimension geometry of topology is 3 and 4. For me, low is 7 or maybe 8. It's super. So 3 and 4 will sit inside the 7th dimension as a kind of Lagrangian, since it's half-dimensional space. And you can see you've got lots of like sky relation. One should be realized as some triarity thing inside. Okay. So now is finally, we have to say what the G2 manifold is. Okay, so again, we start with the most basic, which is just a vector space. And let me just recall the analog here, which is just a K manifold, very quickly. Okay, so let's look at a vector space, V. What we are thinking of is just the tangent space of a manifold X at a point. So we have all Riemannian manifold. So it comes with an inner product. So let's start with the inner product vector space. But the way that we're going to look at a compatible complex structure is slightly non-traditional. So we're going to regard a linear complex structure. So J is a linear map from V to V. This is turned out to be equivalent for the following descriptions. So J is a map from V to V and satisfies the following property. So it is a notion about turning 90 degrees, meaning that you have to start with any V. When you act on by J, the length has to be preserved, and that angle has to be perpendicular to the original. The direction has to be perpendicular to the original V. That's the definition, and that is equivalent of J being a Hermitian complex structure. Okay. And the automorphism group of this linear structure is just a unitary group. And if you have such a structure on every tangent space, so you have J on every tangent space, and then when you move from point to point, this is covariant constant. And that is the equivalent of saying that the manifold is a Kähler manifold. Okay. And another way of saying it is the holomorphic group is this symmetry group. It's a unitary group.
Bravo.
Yeah?
Bravo.
All right. So now you have a Kähler manifold. What are the objects? So there are many objects that could be holomorphic manifolds. But let's look at the submanifold on this point. So submanifold is called a complex submanifold. It's the same as saying that each tangent space is preserved by J. It's obvious. And but it's more important and more useful is it turns out that it is calibrated by the Kähler form. So what is the Kähler form? Omega. It says this. We start with the inner product G. We have a J. And then just put two together. And it's called omega. And omega, in this way, omega is skew symmetric. And that's called a Kähler form. So in fact, once you have a metric, you can interchange these two types of structure, complex structure and omega, which is so-called symplectic structure. So the complex and symplectic structure is related by G in this way. And the complex submanifold can be characterized differently by saying that it is calibrated by this omega to some power. And as a corollary of this amazing lemma or theorem, is this is in particular absolute minimum submanifold. And this is one of the best theorem that I like, because the proof is shorter than the statement of the theorem, if you have seen it. And this is in this foundational paper that I mentioned at the beginning in 1982. Okay, so what I will concentrate on is the lowest dimensional case with the Riemann surface. The sigma is two-dimensional, or the complex dimension of this submanifold is 1. Because in all the other cases, this is the only situation that will be that can arise. So those will be called instantons in string theory. Okay, now we finally go to G2 manifold. Here's the definition. Okay. So the definition is just an obvious generalization of what we have for Kähler. The only difference is instead of sending a vector to another vector, it's a product. You send two vectors to a vector with exactly the same condition, like 90 degrees. So what it means is if you take two vectors, then the product you have to say something about its direction and the length. Okay? The direction is just perpendicular to the original vectors. The length is the area of the parallelogram that these two vectors span. Well, if you look at this, it's not something so new. Everybody have learned this since the elementary school.
Not here.
I'm sorry, maybe here they learn it in kindergarten. All right. So the first one is just a standard vector product, or some people call it cross product, or R3. This for everybody knows this. All right. And the way that one describe it is you consider R3 as an imaginary part of the cotangent. Then the product is just a cotangent product. Of course, you have to project it back to the imaginary part. So that is the definition, right? The one that we know, example. If you look at this, there's an advantage that you immediately get another one. Instead of cotangent, you can look at orthogonal. Same definition. So you look at orthogonal, then the orthogonal product project to the imaginary part is the product satisfied this. We call it two vector cross product. Two referring to you look at two vector and then get it. Okay, and then the automorphism of this is the same as the automorphism of the orthogonal, because this fixed orthogonal product in the imaginary part, and then because you use the metric in the real part, then it's also fixed. So it's the same automorphism. And that's why the group is also G2. Okay, so the next thing is, let me give you the whole classification of all these products. And the answer is there's no other. So this is it. If you look at vector product, either cotangent or the orthogonal, the imaginary part, that gives you all of them. So here's the definition. A manifold with this structure on each tangent space, and you move from point to point, is parallel. And that is called G2 manifold. So G2 manifold has to be a 7-dimensional manifold with such a product at each tangent space, covariant constant from point to point. And what is the analog of a complex manifold? Now, it's obvious, because you have to be preserved by the product, but there's no other product, either it's 7-dimensional or 3-dimensional. So the only thing that can be preserved by the product is 3-dimensional submanifold. So that's what we call that's what we define as an associative submanifold. So associative submanifold is some submanifold that each tangent space is preserved by the product, except by its 3-dimensional. Yeah.
Tangent space.
Each tangent space, yeah.
And this is after you project on the imaginary, which was your
The definition is already in the imaginary part. So when you say product, the product is 7-dimensional. The product is on the imaginary part of the orthogonal.
So the product you mean is you take the product and project
Back to it, yeah. So the product is defined as the vector product is a quaternion product and then projected back.
You mentioned 3, that's a Lie algebra. Is it also in the mixing set of Lie algebra?
Well, G2 is a Lie group, yeah. Or the 7-dimensional, no, it's not the algebra, yeah. Because it's not associated.
It doesn't sound like
Okay.
You take 2 vectors and then you get a third.
That's right.
And you're asking just, that's what this does, it's like a cross block. You take 2, put together, you get a third one perpendicular to that there. And are you saying that the 3-dimensional submanifold is one where any 2 vectors on that submanifold when they cross will give you a third vector that's also a tangential submanifold?
That's right. That's the definition of the associative submanifold. Just like complex submanifold. It's each tangent vector, when you trade of it, it's still living in the submanifold.
Yeah.
Right. So it's the same
The
that
algebra
way.
on the submanifold, you should call it the cotangent. But associative, probably it's just the infinitesimal analog.
Yeah.
Associative.
Yeah. So it's called associative submanifold.
It's the same.
You didn't say why it's called
Very good.
No, I know, I don't
It's
know.
not.
No, I'm just checking.
Are you pumped?
Why do you call it associative?
Stay close, associative. It's associative.
Because if you take that plane and you go back to the full Altonians and add the identity, you get an associative subalgebra. These are the associative subalgebra.
Thank you very much.
So if you take this 3 plane, which is called the associative 3 plane, and just add the identity, you take the direct sum, the identity
Oh,
direct
think the R7 in R8.
Yeah, think of R7 and R.
Oh, yeah.
And take the 4-dimensional thing you can get by adding the identity. That's an associative
Or
algebra.
just taking frame and right down to the associator. Which is there. Frame is.
But yeah. Yeah, there's a natural vector value equal the associative, x, y, then times c, and
Right.
move the other way like that.
Okay, so just like before, a complex submanifold is also can be characterized by saying that it's calibrated by the Cater form. So now, a associated submanifold is equivalent of saying that it's calibrated by the analog of the Cater form. And the analog of the Cater form, same definition. Everything go up 1. Instead of 2 form, now we have a 3 form. Okay? The definition is exactly the same. That you use the product and the matrix and then turn it into a 3 form. It's the same thing. Okay? So everything else is the same. So it's calibrated by a 3 form, and let's call it 3 form. Let me just give you the analog of this 2 product, 1 product, and the 0 product, which will be used later. That's why I have drawn an analog here. So the G2 case is a free form, closed free form in fact. And the calibrate called associative submanifold. And then the Taylor case is a two-form, the calibrate holomorphic curve. If you draw the analog here, then the zero product will be one form, that's a closed one form. And then what they calibrate are those, so if you think the closed one form is exact, let's say g of the function. And then the thing that they calibrate are the gradient flow line. That will be pretty important in the next slide. And the gradient flow line are the instantons when written have his paper on the Morse theory around the same time, I think, 1982 in GEG. Okay, so now we go to a boundary value problem that I just mentioned, that when you have a holomorphic curve, the boundary should lie in the Lagrangian. Why? Because in a case, if you have a Taylor case, if you have a holomorphic curve in a Taylor manifold, they're calibrated by the omega. And why work? Well, because you do some integration. Now, if you do the same argument, when you have a boundary, when you do the integration, you have boundary contributions. You have to make sure that the boundary contributions do not destroy your minimality. So you want omega to vary from the boundary. So that's first condition to make sure you still get absolute volume minimality. On the other hand, if you want the boundary to be as large as possible, so you have more freedom to move the boundary, or move the holomorphic curve. And the largest dimension that this can achieve is half dimension. So those are called Lagrangians. And in fact, you have a fractal field by imposing such a free boundary problem. And thank you. You never know how much I pay these days. And they are called in the open string theory because, as I mentioned before, when string theory, that the boundary, natural boundary value problem is exactly this. And now you have a holomorphic curve with boundary Lagrangians, and the important subject in symplectic geometry is Lagrangian intersection theory. So Lagrangian intersection theory we will study if you have a lot of Lagrangians, let's say 2 of them, and that is you want to count the intersection point in a generalized sense. So therefore, if you have a holomorphic disk where the boundary lie in this Lagrangians, you count those. And those have satisfied lots of all this sophisticated structure property. And then they form a so-called Fukaya category. And that has been an intense study. I mean, to make all this well-defined, sometimes you have to write about several thousand pages. But anyway, this is the basic thing that you need, is to count holomorphic curve where boundary lie in the Lagrangian. And the Fukaya category is a structure that kind of encoding a lot of symplectic information, non-trivial, so quantum information. And the Kontsevich has this homological mirror symmetry conjecture in 1994, says that, in fact, the mirror symmetry should be formulated in saying that there is another Calabrian manifold, extract, that the complex geometry is equivalent to this symplectic geometry of X. So it's an interchange between symplectic geometry and complex geometry on a different Calabrian manifold. So this kind of problem is related here by counting holomorphic disk with Lagrangian boundary condition. And there are many successful cases that it has been proved. For example, even the Calabrian quintic threefold has been largely proven by Sheridan recently. And they all rely on reducing, could be a very sophisticated way that eventually reducing to a case that we can understand better. In that case, the symplectic manifold is just the cotangent bundle of any manifold. So if you start with a space B, any manifold, this cotangent bundle has a canonical symplectic form. Okay? And then in this case, one can describe the Fukaya category. In general, it's very difficult. But in this case, this is equivalent to a category on B. It's the Morse category. So what's the Morse category? Well, Morse categories objects are Morse functions. So you start with a Morse function on B. Okay. Then it immediately gives you 2 different Lagrangians in the cotangent bundle. Well, the zero section is a Lagrangian, always. Okay. In cotangent bundle. Another one is if f is a function, df is a one form, meaning that it is a section in the cotangent bundle. So therefore, the graph of df is another called Lagrangian, so it's kind of like this. So you have a zero section, have horizontal, and then the graph of the closed except one top, and then the Lagrangian. So this two Lagrangian has a nice property that the intersection is exactly where df is 0. So the intersection points are exactly the critical point of the original Morse function. And then the Morse category will be related to counting gradient flow line between critical points. So that will be counting, you pick two critical points and then count the gradient flow line in B. And why is this has something to do with the Fukaya category? It's the following. If you just move the Lagrangian a little bit, so look at instead of f, look at a very tiny particle of f, just epsilon times f. So these two Lagrangians are very close to each other. The critical points are still the same. So if you are very close to each other, well, let me make it bigger so you can kind of see how close they are. So bigger now. I don't have that much money now. Okay, now this is supposed to be very small, and then now finally it becomes so big. So we start to have one Lagrangian, and then a nearby Lagrangian, they're very close to each other. And then what the thing is that if you start to have a gradient flow line in M, in B, so there's a Morse function in B, okay, and then this is a gradient, so this blue part is a gradient flow line in B. And then J of it, because it's a Lagrangian, J of it has to go up. And then in fact, this is to the first order, it's pointing to the L1. So the curve from roughly moves to that direction. And then that is almost close to the holomorphic disk because it's moving by J direction. So it's almost like a holomorphic disk. And then you argue that, well, you have to do some LP estimate to prove that you can perturb it to make it a holomorphic disk. Of course, this is a singular perturbation because the disk is also very small. The two Lagrangians are very close. So you have to do some estimate to make sure that you can apply the implicit function field. But it's not that difficult in this simple case. And then the thing that they have to prove in the paper is you have to prove that this is really true in identification as an infinity algebra. So that's actually long. So basically, this is the idea that these two categories are related. So on the Fukaya side, this is kind of holomorphic curve. On the Morse side, they are counting gradient path. But both are instanton in different sets. Okay. One is for zero vector product, one is for one vector product. Now we go back to the case that we are interested in, a G2. So again, in this case, we will be counting associative submanifold, three-dimensional submanifold in M, and also with boundary. The boundary will be in a submanifold called C. Okay? So let's see what boundary condition does impose. Well, exactly the same. So you want it still to have the calibration well, meaning that you still produce absolute minimum submanifold. So make sure that this calibration form has to vanish there. Okay? So therefore, we require this G2 form, which is a free form, has to vanish on C. And then the biggest dimension this can be possible is C is dimension 4. Still roughly half of the dimension. So those are called coassociative submanifold. So coassociative is half dimension in 4, and where the free form vanish. So this is still a fractal field, so it's nice fitting. And so now we will look at the analog of the study of the Fukaya category in the simplest case, where we count associative submanifold, which we call instanton, but the boundary lying inside the coassociative.
Can I ask you a question?
Sure.
The previous slide, when you said Fukaya-Oh proved the special case, counting the gradient flow lines, how does it help us to understand the complex geometry of the mirror site? These obvious questions are.
This is a long story. So the thing is that this side is very difficult to compute. And in many cases, for example, in the toric case, first of all, people prove in the toric case, we know what the generator for the derivative. So you have to calculate both sides. So this side is the thing which are morphing to the car.
What are the complex submanifolds of the mirror set? At least.
Not in this case. In this case, you see both, because in the toric case, you can go from B to both the symplectic side and the complex side from the same direction. This would take me. You have to take anything, sorry. Okay, so now come back to this case. The situation is like before. Earlier we start with a Lagrangian and move to a nearby Lagrangian and then count it there. Now we need to understand what happened for coassociative. We start with a coassociative C, and then we'll move a little bit. Okay, and let's see what happens. So how do you move? Well, first have to know the normal bundle. Let's look at the symplectic case first. That is well known. In the symplectic case, if you start with a Lagrangian, then the normal bundle is just a cotangent bundle. And so therefore, the nearby Lagrangians, in fact, not just infinitesimal, all the nearby Lagrangians are graph of a closed one form. So they're controlled by closed one form. So everything basically the same. You change from 1 to 2, 3 to 4, everything, right? So now you have a coassociative submanifold here. So the normal bundle, instead of one space of one form, a space of two form, too big. The only space of self-due form. The space of self-due form is the normal bundle for every coassociative submanifold. And that's why it's more interesting. It means more related to like the anti-self-due field. And the infinitesimal deformation is again closed self-due form, just like the other case, but this is only infinitesimal. Okay, so here's how we go explicitly. So we start with let's say you move the coassociative, it's a family of coassociative. So the C dependent on one C. Okay? So you have the normal vector field called N, so this is according to the normal. Okay? What it is that if you contract the free form with the normal vector field, you're left with a two form. You go from free form to two form, and it turns out that this two form is automatically inside a self-due form. So it's a self-due two form.
So,
yes. Yeah. So this is. So that's how you realize the normal bundle is a space of self-due two form. And this is important. So start with this self-due two form. The thing is that if you normalize a self-due two form to norm 1, so let's do that. Then this is like a Taylor form. So if this is a self-due two form, you use exactly the same definition like a Taylor form. And then we come for J. And the norm being 1 is equivalent of saying J squared is minus 1. So therefore, on the coassociative submanifold, if
That's a value of A, is that a function or a constant?
where's A? Eta. It's a two form. It's a self-due two form.
I know, the absolute value, is that
It's a number. Yeah, it's just a
constant or a function?
or at this point, this is it's a function in general. Yes, it's a function. Yeah. So you do it at each point. You say function.
Once they close.
It's not closed. So that's why it's a almost complex structure. If you do not normalize it, it's a symplectic form. So the two ways of doing it. If you do not normalize it, then you can find a compatible complex structure, but then the metric you have to scale it. It's not the reduced metric. Or just fix the original metric, then we normalize this, then you get an almost complex structure. It doesn't really matter for us later, you will see. So you see that the form manifold, the coassociative submanifold, when you move a little bit, you automatically get an almost complex structure. Well, assuming that eta never is 0. Well, otherwise you cannot normalize it. So this is a result, joint work with Wang and Zhu. Zhu is so in fact, the collaboration is I make the observation up to this point that everything should look like a symplectic case, and then we're the one that will carry out the analysis. Yeah. So if you have technical questions, then you have to pay them. Okay, I can get it 20%. This is, I think, who appears soon in JD. Yes, that's everything. So we are assuming that this deformation, the eta is non-zero. What does that mean? That means that if you move this coassociative submanifold, they don't intersect. At least in the test mode, they don't intersect. Why you need that? You have to make sure that the later analysis, all this metric and complex structure are non-degenerate. Otherwise, I will explain in a second the issue that you will face. Right? So the statement is the following. The first part is kind of simple. It's very similar to previous case. The previous case is when you look at very thin holomorphic disks, this is roughly like the gradient flow line. So the situation is when we look at very thin associated submanifold, it looks like a holomorphic curve inside the form manifold, roughly. Okay? So that to make that work is much more complicated, as I was explaining.
So this is the Morse analog.
The Morse analog, yes. So the holomorphic curve is an analog of gradient flow line. And then the holomorphic disk now become associated with submanifold. But the analysis turned out to be completely different. So the first part is just when you have a family of this way, squeezing the associated submanifold, eventually you just get holomorphic disk. That's easy to do. The thing is the converse. If you have a holomorphic disk, let me just sorry. So the statement is if you inside this coassociative submanifold, if you move a little bit, so using these directions, and then you get a complex structure because of the deformation. You get a complex structure. Once you have a complex structure, if you have a holomorphic curve, any holomorphic curve, then the normal direction roughly will tell you that how do you swap out something which is almost like an associated submanifold. Nothing deforming, to be honest. So the assumption, we are assuming that they don't intersect to make sure that the holomorphic structure don't degenerate. And this holomorphic curve is regular in the sense of deformation. Okay? There's no obstruction. So if you start with a regular holomorphic curve to begin with, then you can really swap out a associated submanifold, excessive one. So the next question will be counting instanton. Well, of course, we don't know how to count instanton because we don't know how to do compactness. But if we can do compactness, but at least this film is local statement, just one-to-one correspondence. Okay? So if the counting of such so-called thin instanton, thin meaning that we are ruling out the possibility of having a big bubble. Okay? Forgetting if a big bubble, so the total volume is small, okay, of all this. Then instanton in the second manifold bounding this C is the same as holomorphic curve in C0. Okay? Assuming that non-degenerate. Okay? And then this has been studied in this important work of Taft that said that this Promotion invariant on four manifold, if this is symplectic, is the same as the Calibrations invariant for the four manifold. But why do I want to point this out? Because to define the middle guy, the holomorphic curve, Promotion invariant, we need to have a symplectic structure. But the Calibrations doesn't need one. So presumably, we can bypass all the middle guy. We can ask, can this associative manifold, whether the 2C intersect or not, should directly be related to the Calibrations invariant. Presumably that is the case. So that is why we expect that to continue the whole truth. Even the middle guy is symplectic form will vanish. So that is what is that here. So when they intersect, they usually will generically they intersect along a bunch of circles. So that's where the self-two form vanish. Okay? And in fact, Taft says
circles right dimension because it's 4, intersect 4 instead of.
That's right. That's right. So that's why just like self-two form. Self-two form is a free equation, right? Self-two form vanish will be a circle on the form vanish. So that's where the complex structure vanish. It's not a complex structure anymore. Okay? And then, in fact, this Cliff Taft has made a lot of study about how holomorphic curve can have boundary behavior there. So that is a rather non-trivial subject to do all this hard analysis. Okay, so let me give you an example of how to use this result. And to get some associated submanifold. So let me. So let me start with the good example of G2 manifold first. So I'll start with a Calabi-Yau threefold. So what is a Calabi-Yau threefold? It's a Cater manifold. This is something that we know already. With 6-dimensional remaining manifold, complex structure, symplectic structure, everybody is nice. Okay? Together with the property, the rigid curvature is 0. So rigid curvature is 0 under some topological mild assumption. It's the equivalent of saying that you have a parallel holomorphic volume form. Okay? It's a free form because it's a complex free form. So let's just call it capital omega. It's a free zero form. It's like DC1, DC2, DC3. Okay? And then once you have that, the 6th manifold, you can cross with a trivial direction. Let's just call it S1 to get a 7-dimensional manifold. Okay? And that is the G2 manifold. I'm just writing down the G2 form here. The G2 form is combining, it's a free form. So it's combining the holomorphic free form on the Calabi-Yau free form and the Cater form, which is only a 2 form. So therefore you write with the d theta, which is the circle direction. Theta is the circle coordinate to get a free form. And that is the G2 form. You can go from G2 form to the vector form, if you like. Okay, so this is a picture. So we're thinking about you have a family of Calabi-Yau threefold fiber over the circle. All right. So here are some examples. If you have in a Calabi-Yau threefold, you have a complex surface. Everything is complex, right? So complex Calabi-Yau threefold, a complex surface. It's a real 4-dimensional. And then if you put that inside any slide, so C is inside Y. So if you C cos any theta, so inside Y cross circle, that is coassociative, 4-dimensional. So you look at C cross any particular slice, okay, then that will be a coassociative. How about associative? So the instanton. Well, you start with a holomorphic curve, and then cross with the whole circle, so that becomes 3-dimensional. Okay? That is associative. So this is the picture I draw. You start with sigma is a holomorphic curve in one of the slides, and then you product. Okay? Make it 3-dimensional. So that's the 6-dimensional. That's 3-dimensional. And so these are the trivial examples. So if you have a complex surface and a curve, so you can look at the complex surface of one side and another side. Okay? You look at curve inside, you cross it. So you get the associated submanifold whose boundary in coassociative. Trivial example. How to make it non-trivial. Okay. So again, to make it non-trivial, we're going to find holomorphic curve inside complex surface inside Y with some condition. Well, the condition is the sigma is the curve is a canonical curve in the surface, and PG of the surface is 1. Well, it's not that important if you don't know everyday geometry. But the condition is to ensure that the curve inside the surface is regular. This is just a Riemann-Roch type argument. And also to make sure that you have deformation. Okay? So the surface also can deform inside Y. That's you can just check what you need, and that is the condition. Okay? So now the surface moves inside Y. So when they move, they intersect. Okay? But if you put in different slides, then they don't intersect. Okay? So therefore, if you move the surface inside Y, so cos C, and then you move a little bit, cos CX. Don't have to be a little bit, right? So they usually intersect. But if you put in different slides, one is putting 0 slide, the other is putting epsilon slide, any epsilon. Then they don't intersect. Okay? So the picture should roughly look like this. You put, oops, I only saw something so big. You put one Y, another Y, 2 different slides. In one of them, you put C, and then the other one, you move a little bit already. So CS, that's what it was. On the C, you have a holomorphic curve sigma inside, but which is regular. When it's regular, it will still move in here. Because regular, making the deformation will move along. Okay? So therefore, if you move to a generic JS, because it's regular, so all the sigma will also perturb along. So this is the picture that I draw a moment ago. Then our result will tell us that along those directions, you can find this instant going through one through the other. It's not. This is not exactly joining to JS, but instanton will move a little bit. This is the first order is like joining the whole family. But then once you perturb it, it's not like that. This is very close to that. So that is what you can construct example, which is not directly coming from another field.
Oh, well, where's the four manifold?
The four manifold C. This is the association. Yes.
But I mean, there's a unique associative that contains sigma, right? I mean, it's a surface it's a real analytic surface inside the
C is associative.
It's a real analytic surface inside the submanifold. And
So that means C or sigma.
Sigma.
Okay.
It's a real analytic surface inside the submanifold. And the theorem of Harvey and Lawson says that it can be uniquely thickened to an associative.
But they need to heat the other boundaries. You have to heat the other boundaries, special associative.
Yeah, but the point is that because there's a unique thickening, you can't.
No. See, the thing is, once you perturb, this is not going to be sigma anymore. So let's pretend that these two. So the thing is,
Both of them move.
yeah. Both of them. If you are very close to each other,
Yes.
right? Then you think that this is just family of sigma. So let's just pretend this is very close, right? So you look at this family, right? This is when they're very close to the associative. But then you
in general,
it's not associated. You do a perturbation. The perturbation, like here. So it's not going to be sigma anymore.
Yes, they would have. But the point is, you could make an associative name just by taking one endpoint, and there's a unique actual
But
associative.
they don't hit the boundary though. You don't hit the coassociative. You fix
No, it meets the coassociative transversely. The associative guy has to meet it transversely, sure.
They may not meet it at all.
No, well, if it passes through sigma, of course it does.
No, this one will, but the other one you may not meet it.
No, in general it won't.
Yeah.
But,
So that's why we will prove that you can hit both boundary conditions. The coassociative will have
I'm
all
not
the
sure I
boundary.
believe it can hit both boundaries. I mean, if it hits one of them, if it passes through sigma,
Yeah,
that's
it's not going to pass through
specified.
sigma. The point is, it's not going to pass through sigma. It has to be. See, the thing is, the thing you start with this one that pass through sigma, but that is not coassociative. So you have to perturb it. The perturb it will be like this. It's not going to pass through sigma anymore. I mean, all the scale is very small. I mean, if it passes through sigma, then it's unique way to extend it, of course. But then you won't hit any coassociative. So when you fix this coassociative, you want to count the holomorphic associative inside and between. So start with something which is like that, but not associative. After you perturb it, it will go away from this associative. So this one is not going to the holomorphic curve anymore. Right. Okay. Is that okay? Should I take you something? Okay, let me just give you let's just point out a few key issues that are involved here, which is very different from the Fukaya case. Okay, so the statement is what we really try to prove is this one. Then we start with a holomorphic curve, and then you want to, if you move the C a little bit, you want to claim that you get an associative manifold. Right? So the picture is like this. You start with, you fix M, and then you have a family of C. There's C0, Ct, and so on. Okay. So again, the normal direction will give you a self-Q2 form, assuming that it never vanished, so that they don't intersect. Okay. So then you get almost complex structure on C0, and then you have a holomorphic curve with respect to C0, this almost complex structure. Okay. And then once you do that, you use this normal direction. You can just choose some way to roughly move it, and then to swap all the three-dimensional submanifolds with the right boundary condition. But it's not going to be associated. Rachel is close to B. Okay. Let me just say again. Then you perturb. But when you perturb, everything. Okay. So this is the picture. You start with sigma, and then you swap it out to get something which is almost instanton. And then you hope that when smallest, when you move always tiny little bit, then you can really honestly, particularly honestly associate. So here are the key difference. The basic philosophy looks the same as before. We start with gradient flow line, J of it, move it a little bit, perturb it, right? In the case where you argue gradient flow line count is the same as holomorphic curve physics. Okay? So this is what Fukaya-Oh proved that. There are several main differences here. The first one is this is now become, yes.
I was confused during that last part a little bit because when you kept saying instanton, I kept thinking of the instanton of the fallacy before. So you're using the word instanton for any of these canonical objects.
That's right.
J holomorphic curve.
J holomorphic curve or associative manifold.
Associative, everything is an instanton.
No. The instanton is holomorphic curve or associative manifold. The boundary value are called Blaine.
Okay.
So the Lagrangian are coassociative.
Is there any relation to Lawson indices like self-dual connections on?
Not that I'm aware of.
Except that you put them on the four manifold.
I can tell you more about why there will be instanton in terms of some semi-infinite dimensional Morse field. Okay. So there will be a gradient flow line in some infinite dimensional Morse field. All right. So okay. So the analysis on the surface they look very similar. You look at gradient flow path, flow line, J of it, roughly a holomorphic curve, perturb it. So the first difference here is that now we are doing a PDE not in 2 dimensions and 3 dimensions. And then you don't have conformal symmetry to help you. Why do you need that? Well, first of all, because in a holomorphic case, you look at holomorphic this way, it's very, very thin. So you look like you have a singularity near a boundary. But after conformal change, it just looks as well as this. Okay? We can't do anything on this. So that is the issue. There are a couple other very important issues. First, the equation is more linear in the holomorphic curve case. And linear equation help a lot because when you do LP estimate, when you do the tensor, when you look at the product of those terms, don't still inside the LP. So if you have nonlinear equation and the quadratic index is cubic term in the nonlinear term, then you need to look at the product. The LP will destroy. So therefore, you can't do an LP theory. We have to do a pointwise Schauder estimate. So that makes the analysis different. And also, because we lose the conformality, the equation that we look at is also not uniformly good. So there are all kinds of issues. So this is roughly, instead of the LP type this integrated action estimate, we need a pointwise estimate. An estimate is on a direct operator on a 3-dimensional manifold. But the thing is, the 3-dimensional manifold itself is degenerating. So the 3-dimensional manifold, the Riemann surface, cause a very tiny interval, and that is going to 0. So let me say, okay, I can say a few more on this. So let me tell you how to characterize this. And this is of course, in this original paper by Lawson. That you can find, first of all, you have to be able to describe the instanton better. Calibration is a powerful way to construct minimum submanifold, but you want to write down an equation that is not as useful. So you want to write it as 0 or some form or something. So this is how you do it. The instanton, a 3-dimensional submanifold is an instanton if and only if the following tensor vanish. So what is the tensor? You start with the free form, omega. So star of the free form is the 4 form. We call star omega. And then you either, I don't know, I think it's raising the index. Either raising or lowering the index. You change the 4 form into a free form with tangent value. Okay? That is called tau. And the vanishing of the tau is exactly the associative submanifold condition. Furthermore, more important thing is that in fact, is the normal direction. So that will be important because the deformation of associated submanifold is also deformed in the normal direction. So you want to tell you that the equation is also equation on the normal direction. So first of all, what is the normal direction? You
What
can,
was tau in that previous slide?
so tau is defined as the following. If you start with a free form, you look at the start of the free form as a 4 form, and you raise the index to make it a free form with tangent.
Well, the variable goes up,
Yes, sorry.
or something.
Yeah. So this is a defining equation for tau. So the tau manage is the equation. So that is a, you can write down PDE. And so how to
Capital
define it?
omega in that class.
Sorry?
What's capital omega?
Capital omega is a free form. So G2 manifold is
Defining free form.
defining free form. That's right.
Okay. I see, it's the same thing, tau and omega are the same thing. I mean, they're just
Yeah.
same information.
Same information.
Okay, fine.
Yeah. Because omega determines everything. So now you want to say that, well, because you don't need to deform we start with something which is close to the associative, and then you have to move it. So how do you move it? You need to understand the deformation theory of associative and manifold. It is slightly more tricky than coassociative. This is controlled by a direct operator. Maybe not suddenly go much faster because I only have 3 minutes. I have a little other thing I want to say. So anyway, you can set it up like this. So you start with holomorphic curve, okay, on C0, and then sweat out something which is like the associated submanifold. But that's not real. You have to move it a little. Okay, bear in mind everything is small, so everything is degenerating. Okay? So how do you do this? So you move in normal direction, and then the equation is tau with strict to it is 0. And tau is what? Well, tau is also, with strict to it, is also in normal direction. Free form or 0 form doesn't really matter. You can start it becomes 0 form. So therefore, the equation is just f equal to 0. So f sending you deform in some v directions, and then you exponential the submanifold, and then restrict the tau to it, and asking whether it's 0. So just say that, just set up the equation where f is 0 is associated submanifold, and then you try to do a singular perturbation. And then there are all this key argument here, which I'm going to not be able to have time to explain it. So anyway, you have to do a lot of this Schauder type estimate, and especially taking care of the domain is degenerated. In fact, Zhu right here will be the person who would be able to better answer this technical question there. Again, we will look at uniform multiplicity and all this nonlinearity, make it difficult. So you do all this and then do a qualitative version of the implicit substitution theorem. That is what you need to do a singular perturbation. So that is all this argument that of course I have given you the geometric picture which I provide. And then
Qualitative, quantitative.
quantitative, so. Because you need to look at stats, yeah. It's a quantitative version of it. So just testing whether you're still okay. So let me say a few words in the last few minutes about general vector cross product. This is a very simple observation earlier. Is you can define the vector cross product as before, just the same. Instead of two vectors, put to one vector, you can look at a number of vectors. So it's called our vector product. Just look at our different vector, put to one vector. Okay, it's the same definition, nothing changed. And instanton, exactly the same, nothing changed. So first of all, it is preserved by the product, or equivalently, this is calibrated by the output one form. Same form, same definition. Now you know everything about calibration geometry. Okay? And also, you can also characterize it in terms of this analog, the tau, being 0. In fact, in all this individual case, they have written down here. Tau is the following. It's not the same way that we define it in the G2 case, but it's a general definition. It's an output1 form with value in some vector bundle. And the vector bundle is a subbundle of space of 2 form. And G is a subbundle which preserves the cross product infinitesimally. And you look at the curve of that. So that works in all the G2 and spin-7 And the vanishing of this tau is this equivalent. And that will be the equation that you use to analyze any of this modular space. Okay? For instanton. And then Blaine again is the same, that this is the largest possible dimension where the omega can vanish. And this is the largest possible dimension. And the study of Blaine is because the boundary of the Instanton is in the brain to get it home. So these are the classification. In fact, if you even allow all the vector cross product, not too many. We have studied Kähler case. That's why you have Kähler manifold. Instanton is holomorphic curve, Blaine is just Lagrangian. And then we just talk about G2 case. So Instanton associates submanifold, Blaine are coassociative submanifold. And there are two more. One is a very trivial one. Basically, the volume form always gives you a vector cross product form. So that's a kind of trivial case. In that case, everything is calibrated. This is top dimensional space, of course. So it's nothing interesting. And the boundary of a domain was a hypersurface. That is the obvious thing about boundary, right? And there's one more on trivial case is a spin 7, as I mentioned earlier. And then in that case, Blaine calibrated submanifold called Kähler submanifold, which is in the paper. And in that case, Blaine doesn't exist. They're just too restrictive to allow any Blaine to survive, even from linear algebra point of view. Okay? So you can analyze all this from a uniform perspective. And the one that are being highlighted are those which are calibrated. Those form constructed, calibrated are those manifolds. And the first thing is the first two examples work in any dimensions. For Kähler case, work in all different dimensions. And the volume form, too trivial. I mean, basically, not interested.
Except for hydrodynamics.
Except for the next transparency. The next one said that if you want to complexify the whole setting, these are the most interesting. Because when you complexify volume form, what do you get? You get a Calabi-Yau manifold. When you complexify symplectic form, what do you get? You get a Kähler manifold. So therefore, when you look at complex vector cross product, basically the same definition, instead of real vector space, you look at complex vector space. Okay? Do exactly the same thing. You get complex vector product. But now, it only survives in these two trivial cases, volume form and symplectic form. You don't have a G2 and spin 7 analog. That's from linear algebra. That's the only two possibilities. So this classification, in this case, you only have the volume form, meaning that you have a Calabi-Yau manifold, and then you have a symplectic form, then you have Kähler. Now, Instanton becomes more interesting. In the case of volume form, of course, Instanton is not interesting because it's what is calibrated by the volume form, which is any domain. So nothing, right? But now, because holomorphic volume form, so this is half dimension. But it's a complex form. So you take any angle, let's say real part of the holomorphic volume form. Now the Instanton will be calibrated by the real part of the holomorphic volume form. Okay? Or the real part of the holomorphic symplectic form. And then those will get special Lagrangians or holomorphic curve. Okay? Now because you only calculate half of those because you take a real part or imaginary part. Now there are two different boundary conditions. You can impose a Dirichlet type boundary condition or Neumann type boundary condition. And then the Neumann type boundary condition, in this case, will be like a hypersurface, the complex hypersurface. Okay? And then the Dirichlet boundary condition will be in the Lagrangian case. Those will be special Lagrangians, but the angle has been shifted by pi over 2. In fact, this has been studied by Lawson in Rick and all these performance difference. This information was with this type of Dirichlet boundary condition. And then if you do the Kähler case, the Neumann and Dirichlet boundary condition turn out to be even more interesting. They both corresponding to complex Lagrangians, but the Dirichlet condition is complex Lagrangian after you do a twistor location. So, and these are again the ones being highlighted are those which are being calibrated. So in fact, so that a couple remarks here. The first is using vector cross product, this gives you interpretation of all this calibrated geometry, all the holonomy geometry, say classified by Boucher. Or you don't see the quadratics in Kähler case. The way you can think about that is a quadratic version. But in that case, there's no vector cross product. So you can do all this. So that means that a vector cross product is a unified way to describe all the classification of holonomy group, and also give you all the interesting calibrated cycle. They are all either Instanton operator. Thank you very much.
Questions? Comments? Blaine?
So I was sort of hoping you would tell us something about a possible mirror symmetry between G2 manifolds. I realize it has nothing to do with your job.
Okay, how about 10 years?
I mean, the calculation will take about 10 years.
No, there are lots of things. That one of difficulty is that we don't have companions.
Yeah.
On this. But let me, I was promising to say a few words on this. If you start with a G2 manifold, so you get a free form, or star of that is a four form, right? So in fact, if you look at 1 plus omega plus star omega plus the volume form, you can write as e to the omega plus star omega. Or another way, if you like spinor, that is the square of the spinor. Right? That's all known. The thing is that now how do you use this form, okay, to get all the cycle from this perspective? It's the following. You look at M, and then you look at submanifold inside called S. Let's say k-dimensional submanifold. It's not split, just any k-dimensional submanifold together with some bundle, let's say, with a connection. Okay. So let's define the following actions. So what you do is the following. You look at the integral of the curvature, let's say trace of the curvature for plus this, omega plus omega star. Or if you like, you can put a spinor square. Okay? So this function, you integrate from S0, D0 to S and D. So this is a Chern-Simons type, meaning that you fix a background S0 and a background D0, and you fill it by family of space and bundle to integrate. Okay? So it's the same as Chern-Simons type constructions. Look at this in action. Kind of obvious, right? But it turned out to be extremely interesting. In what way? Well,
Because they're all different dimensions of the exponents.
yeah. So that's why you have to integrate to get the number. So the form has to be the right dimension.
Right terms.
Yeah, so I'm going to say there are only 3 cases that you can put in the right dimension. Yeah. So the 3 cases you can apply is the first case is 3-dimensional submanifold inside M7. The second is 4-dimensional submanifold inside M7. Or 7-dimensional submanifold is equal to M7. Okay? The 3 cases. This is the only cases that you can get a number. Otherwise, the form just never match. And then what are the critical points? So the critical points in this case correspond to associative submanifold plus flat connections. So like Chern-Simons theory with associative free manifold. And in the 4-dimensional case, you get coassociative submanifold plus anti-self field. So that's quite interesting because anti-self field, if you are in the 4-dimensional manifold, anti-self field equation is not a critical point. You only look at it inside 7-dimensional, then it becomes critical because you use a coassociative deformation to make it critical for anti-self field. Because when you move coassociative, you move in the anti-self field direction, right? So therefore, and then you move in the connection direction to make it coassociative. So now make it both stuff. So it's more. So in this way, the G2 is a better setting for anti-self field than in 4-dimension. And in this case, you get Donaldson-Thomas type equation. Yeah. So,
Say that again.
so Donaldson-Thomas is the following: that if you look at a G2 manifold, okay, 7-dimensional manifold. So on the space of 2 form, you have one part which is a G2 part. Because space of 2 form is the symmetry of metric, and you preserve the G2 structure. So that is preserving that. So of course this is a rank 7 bundle, rank 14 bundle. There's a remaining part which is rank 7 in here. Okay. So the way that I interpret it is a curvature or connection is called Donaldson-Thomas if and only if I think the curvature part is on here is 0. Or the curvature is inside here. So. Yeah, the curvature is inside. So that works for all vector cross-border and long division element. So, So that's the Donaldson. Another way is just so it's the same as F7. This component.
So there's a theory of these on 7 manifolds?
Yeah.
G2
manifold.
The compactness here?
No.
The local.
Yeah.
Local credit.
No, well, I don't know how to do comparison. It takes more than you have to ask me back in 20 years. But yes.
Reese?
In the Morse theory, you have the critical point.
Yes.
Do you have anything to say about a manifold or a stable submanifold? In the other cases?
You've answered it before. You said you could explain to Blaine in terms of semi-infinite stuff, these various.
Yeah, so this will be one. I mean, this is so this kind of Morse function will give you. I mean, so for example, if you look at so not exactly, but let me say here's one example. If you look at this case M7, okay, so this Morse function on the space of all submanifolds and connections, right? And the critical point will be coassociative, will be associative plus flat connection. Okay? And then if you look at the Morse theory from this, the flow line from this, what you get will be the M7 cross out, across the interval. Okay? And then you go from one to another, the gradient flow line will become a KD submanifold in the 8-dimensional space. And then together with the anti-self-field connection on this KD submanifold.
And that would be the analog segment.
Will be analog, no gradient flow line. I mean, it depends whether it's done. I don't. You have to look at what the downward means. Little bit about it.
Any other questions?
So, yes. Going back to the beginning of your lecture, you were talking about holomorphic curves with boundaries on special Lagrangians.
Yes.
So, I mean, part of the analytic theory,
Yes.
I guess would work even if the boundary was on a Lagrangian. You don't need the special Lagrangian.
That's right. That's right.
So, what is the contribution of the special Lagrangian condition?
There's no distinction in G2 setting because in the Calibrations case, you get Lagrangians come from symplectic form, but special is really a complex data. But once you go to G2, the two mix together. In a way, it was reflected by the fact that the free form in the G2 is a combination of both the real part of the holomorphic volume form and the symplectic form. So it's a symplectic and complex all together. So you can't really separate out the two conditions by saying Lagrangian or special Lagrangian. Whereas Lagrangian is automatically special. So you don't have this flexibility in the G2 setting. So it's similar to the fact that if you're in symplectic geometry is so flexible, it doesn't determine the metric. But not in G2 case. Once you have the free form, then the metric is determined completely. So
You
you
raise
can't
the word special or it's on the Fukaya-Oh.
Yeah, so you can talk about all this theory by Lagrangians. You don't have to be special Lagrangians. The whole Fukaya category, you can define it for Lagrangian boundary condition. What I'm saying is that is a theory for symplectic geometry, a theory of two form, non-degenerate two form. If you move to a theory for non-degenerate free form, like Hitchens, open orbit or whatever, the free form theory, then the thing is as coassociative submanifold. It's so much rigid because being non-degenerate free form determines the metric. Everything is determined. In the case of two-form geometry, fixing the symplectic form does not fix you the metric. So if you want to talk about special or minimum, you make a choice of the metric, and that gives you the flexibility. And the flexibility is related to stability conditions on the mirror side. There's this flexibility of, for example, holomorphic bundle may not minimize the raw energy. You need stable bundle to minimize the energy. Because holomorphic has this flexibility. In contrary, in all this Thomson-Thomas bundle, you don't have any flexibility like that. Once you have dollars of commas, it's already calibrated. I mean, or minimum. Yeah, minimum. Yeah. So the free-form geometry is much more rigid.
Other questions? Yeah.
Suppose you, just for terminology of this question, say it's a Pologist definition of the G2 manifold is a manifold which has this closed free form.
Yes.
And that's it.
That's right.
Now I ask, does the metric always exist to give your definition?
That is,
Does
it's
it-
also,
let me finish. And if it exists, is it unique?
yeah. So you start with a free form, okay? For example, a generic free form in the sense of it sits inside an open object. So this is Nigel's definition. The free form,
Closed.
you don't even need the closeness at this point. Okay. Basically, it's a linear algebra statement is that in this open object, then it determines you automatically the metric. Metric is unique.
There exists a canonically associated metric.
That's right.
With what properties?
Uh,
What you said.
with this property, then you get a product, meta product. That's a unique metric, so that when you turn the free form into a product, that satisfies this vector cross product property. That's unique. Just unlike the symplectic case, you take a symplectic form, there are a lot of metric to make it a permutation complex structure, but not in the free form setting. It's unique. So it's much more rigid in that sense.
Any other questions?